Hello, IP Physics. This is Dr. Brenzi, and this is a video on lesson 8.2, which is talking about gravitational potential energy for an object out in space. And we're also going to be talking about another concept called escape velocity. So, gravitational potential energy, we learned way back in Unit 4. Was it Unit 4 or Unit 3? I think it's Unit 3, actually. So way back in Unit 3, we learned that if you know the potential energy function of something over its displacement x, then you can actually calculate the force on that object in that position by taking negative du dx. So if you know the potential energy is a function of displacement, then you can calculate the amount of force. And now that you have enough calculus knowledge to know that you can take the antiderivative of both sides to get a formula for potential energy as a function of force, so if we know how force changes over displacement, then we can calculate how much potential energy it has. So close to the surface of the Earth, we have a formula where F, the force due to gravity, is negative m times log g. And then if we take the, oops, sorry, I forgot my diagram here. So if something is experiencing gravitational force of Fg, and then we try to displace it by a distance x, what will its potential energy become? Well, if we take the indefinite integral, negative f of g dx, what we're going to end up with is gravitational potential is equal to m times g times x plus some constant c. And this looks very familiar, except in the past we've used h for height instead of x for displacement, but it is the same thing. We can also do the same thing with Newton's law of universal gravitation. We can write out the formula for something that is displaced from the center of a mass m, and we try to displace it out here. And then when it is out at this position, it will experience a gravitational force equal to negative big G, big M, little m, over x squared, and I'm using x instead of r here to be consistent with this formula up here, because x is displacement in that formula. And let's go ahead and figure out the antiderivative of that. So what all these things are constants with respect to x, so I can factor all of those out. Oops, I'm a step ahead of myself there. So now I can factor all of these out because these are constants with respect to x, so let's factor them out. And then what is the antiderivative of 1 over x squared? Well, it turns out to be negative 1 over x. So our gravitational potential energy is negative big G, big M, little m over x plus some integration constant c. What's going on with this integration constant? Well, it gives us the freedom to set an absolute, it gives us the freedom basically to set a position where potential energy equals 0. Now, close to the surface of the Earth, what we've traditionally done is we've said, okay, ground level, potential energy is 0, and then we will measure all of our displacements with respect to that position. So if we go up a height h, we have a potential energy U equals mgh. And I got a little ahead of myself here, because now what if I decided to dig a hole in the ground and put this object down below the ground? Well, what would happen is it actually has a negative potential energy. That negative potential energy is now negative m times g times h. So when you're above ground, you have a potential energy greater than 0. And below ground, you have a potential energy that is less than zero. And the only reason that that's true is because we determined that at ground level, the amount of potential energy that the object has equals zero. And that's what we do with that integration constant. Well, what happens with Newton's law of universal gravitation? What happens to that integration constant? Well, the same principle applies, but what we decide to do in physics with universal gravity is that we decide that as r approaches infinity, so as the two objects get farther and farther away, and when that limit approaches infinity, we decide that we want to set that gravitational potential energy equal to zero. Not at the surface of the planet, but we decide to set u equal to zero out at a distance that approaches infinity. What that does is that effectively means that that integration constant is zero. So really the formula that we use in physics for gravitational potential energy is negative big G, big M, little m over R. Now that means that potential energy is always negative. Why would we want to do that? Why would we always want potential energy to be less than zero? It does tell us something. Just like over here in this situation that we're more familiar with, it told us that when you have negative potential energy, you have something that is below ground. This potential energy tells us something. And in order to do that, in order to show you what that says, I actually have to use another picture here. So let's draw this picture. So let's say we have two rockets. Okay. Now, an object's total energy is equal to its potential energy plus its kinetic energy. And there are two possible scenarios we can have. We can either have a total energy that's less than zero. And you're saying, wait a minute, can total energy be less than zero? Well, you're going to actually find out here. And then we can have a scenario where the total energy of the rocket is greater than or equal to zero. So let's look at this scenario over here on the left-hand side first, where the total energy is less than zero. Now, total energy can be less than zero because gravitational potential energy is always less than zero. So on the left-hand side here, we have a situation where if we were to draw a bar graph of this object's potential energy and its kinetic energy just after it blasts off the surface of the Earth, in this particular scenario, it might look something like this. So you have some amount of kinetic energy, but the bar graph for potential energy is bigger and negative. So when you add these two numbers up, you're going to get a total energy that is less than zero. All right, that sounds strange, but what if we allowed this rocket to go out into outer space? So as it's getting farther and farther away from Earth, what's happening is that this bar is actually getting closer and closer to zero, because as you go farther and farther away, this absolute value becomes less and less and less because it's 1 over r. And then the kinetic energy will get less and less and less because we are converting kinetic energy into potential energy. So, but at some point here, we're going to end up with a scenario that looks like this. At some distance away from planet Earth, we're going to run out of kinetic energy. We're going to have zero kinetic energy, but we're going to still have some gravitational potential energy left over. What happens in this scenario? Well, it's going at zero velocity, but since it's still experiencing a gravitational potential energy, it has gravitational potential energy that's negative. The fact that we have some gravitational potential energy means that we also have a gravitational force, right? Because F is equal to negative du dx. So there is a gravitational force when it has gotten to the point where its kinetic energy is zero. But it still has a gravitational force pulling it toward Earth, which means it's going to turn around and start falling back toward Earth. So, in the case where the total energy is less than zero, we don't have enough kinetic energy to overcome this amount of potential energy, which means at some point we're going to have to come to a stop. We're still going to have we're going to still have some potential energy, which means we're going to still have a gravitational force, which means we have to end up turning around and falling back toward Earth, which means we can't escape. So when the total energy of the rocket is less than zero, it is impossible for that rocket to escape. Now, on the other hand, if we have a total energy that is greater than or equal to zero, we have a bar graph that looks like this when we first blast off the planet. But we're never going to run into this scenario over here where we run out of kinetic energy. We're always going to have an ample amount of kinetic energy to overcome the gravitational potential energy that we have left over. Even though we do have some gravitational potential energy, even at very, very large distances, we still have plenty of kinetic energy that we're never going to run out, which means we are free to go wherever we want. We're never going to run into the scenario where we run out of velocity and we have to start falling back toward Earth. And in that case, the rocket is free to escape. So the reason that we have negative potential energy is because we can compare that to kinetic energy and figure out whether or not we're going to be able to escape the planet's gravitational pull. If we're in this domain where total energy is greater than or equal to zero, then we have enough kinetic energy to escape the planet. If we don't have enough kinetic energy, then our total energy is less than zero and we cannot escape the planet's gravitational pull. We're not free. So potential energy being negative gives us the information about whether or not we can escape or not. Let me go ahead and show you an example of how we could put that into use. Oh, actually, I forgot to say something. Escape velocity. So I told you that I would calculate, or I would tell you, how much velocity do you need to escape a planet's gravitational pull? Well, we just learned that if you have enough kinetic energy so that it's greater than or equal to the absolute value of your gravitational potential energy, then you can escape and go wherever you want. So that means that 1/2 mv squared has to be greater than or equal to the absolute value of negative big G big M little m over r. Well, we can solve this for v in order to figure out how much velocity we need in order to escape, given our position. All right, so just take the absolute value sign out there, and then we're going to solve this for v squared. We get 2gm over r, and then we take the square root of that, and that's what we call the escape velocity. So if you are at a distance r away from a planet, this is how much velocity you need at that position in order to escape. And that's famously what's called the escape velocity. Okay, now, you're not going to see this formula on your AP Physics exam equation sheet, which means I'm not going to put it on my equation sheet either, which means you have to understand that this is how you derive it, by using this statement right here. You will be given gravitational potential energy, or you can figure it out based on gravitational force. But you have to be able to derive escape velocity, okay? Because you're not going to be given that equation on an equation sheet in the AP exam. All right, let's do an example here now that we got by that. So here's an example. Let's say that we have a 1,000 kilogram weather satellite, which by the way is a huge satellite. And it's in circular orbit 300 kilometers above Earth. And we're going to first calculate what its gravitational potential energy is, and then we're going to ask ourselves how much more kinetic energy does it need to escape Earth's gravitational pull. Let's tackle problem part A first. Let's just calculate how much gravitational potential energy it has. So we are at a distance of 300 kilometers above the surface of the Earth, which means I have to take that 300 kilometers and add it to the radius of the Earth, which is 6,400 kilometers. So I add those two together. Oops, sorry. Let's go ahead and write down our formula for gravitational potential energy and then start plugging some things in, and it's pretty obvious to me that I'm not going to have enough room to do all this. So I'm going to do that one on another slide. So let's erase that. And let's start plugging some numbers in. So big G is 6.67 times 10 to the negative 11. Then the mass of the Earth is 6 times 10 to the 24 kilograms. And by the way, if it's not stated in the problem itself, you are going to have a sheet that you can use. And I'm going to give you all sorts of facts about planets in this unit. So there'll be a table that we'll use, and I'll introduce that to you in class. But the mass of the Earth is 6 times 10 to the 24 kilograms. And then the mass of our satellite is 1,000 kilograms. And then we divide all of that by, don't forget that has to be the total distance from the center of the Earth. And that's why I have 6,400 plus 300. But those are in kilometers. We want meters. So I have to multiply that entire thing times 10 to the third to get meters. All right, now at this point you could end up punching all this into your calculator and doing a lot of plug and chug. But I'm going to do it the old-fashioned way here a little bit, and I'm going to try to do this by hand, because it turns out I actually noticed something that allows me to do it very easily by hand. So what I'm going to do is I'm actually going to separate these numbers from the powers of 10. So I have 6.67 times 6, and I didn't bother to do this one because I can convert that to 10 to the third. So in my numerator, if I add the powers of 10 together, I have negative 11 plus 24, and then this is 10 to the third, so I have to add plus 3. So 27, which is those two, minus 11, is going to be 16. So up top, I have 6.67 times 6 times 10 to the 16. And then in the bottom, I have 6.7 times 10 to the third times 10 to the third again. Well, the reason I decided to do this by hand is I notice that these two numbers, when you add them up together, they're about 6.67, which is really close to that number. So essentially, those numbers divide out. And what I'm left over with this constant of 6, and then I just have to add and subtract powers of 10, and it turns out I get 10 to the 10 joules. So this satellite has a gravitational potential energy of negative 6 times 10 to the 10 joules. All right, now let's tackle that part B. How much more kinetic energy does the satellite need to escape Earth's gravitational pull? Well, it's going around in a circular orbit, so it has some sort of kinetic energy, right? In order to calculate how much kinetic energy it has, we have to calculate how fast it's going. Well, it's in a circular orbit, so I can use F net equals ma, and remember that a is v squared over r. The only force pulling on this satellite is gravity, so Fg is equal to negative mv squared over r. Comes from our last unit, or actually unit 6, but all right. So let's plug in Newton's gravitational force over on the left-hand side, and then we have mv squared over r on the right. And now we can cancel out some m's and cancel out one of the r's on each side. And it would be very tempting at this point to go ahead and start plugging numbers in. Don't do it yet. This is why I have you work symbolically. Because you're going to find out, especially with large scientific numbers, it's sometimes better to work symbolically and then work your way and then plug in at the very last minute. Okay, so I have something that says that v squared is equal to g big M over r. Well, if I want to figure out how much kinetic energy it has, then I just have to take this and multiply it by 1/2 m, because kinetic energy is 1/2 mv squared. Okay, so now I have an expression for how much kinetic energy it has. And this looks a little bit familiar. If I do a little bit of arranging here, it turns out I have 1/2 times big G, big M, little m over r. Hey, that looks awful familiar. As a matter of fact, that is the absolute value of its gravitational potential energy. Okay. So in order to escape, it has to have a total energy greater than or equal to 0. That's the condition for it to escape, which means its kinetic energy has to be greater than the absolute value of its potential energy, or actually negative U. So its kinetic energy has to be greater than or equal to G, big M, little m over r. Well, we already have exactly half that amount. And that's actually a very famous, relationship, is that when you have something in circular orbit, you have exactly half of the velocity that you need to, you have half the kinetic energy you need to in order to escape. So you just have to be able to double your kinetic energy somehow and you'll be able to escape. You need another 1/2 G, big M, little m over r. And if I remember right, that's 6 times 10 to the 10 joules. That's what this number is right here. That's what we got on the last slide. So you need another 3 times 10 to the 10 joules in order to escape, which is a lot of energy, which is why we don't send a lot of things out into deep space. That's an incredible amount of energy. That's how you could actually calculate how much more kinetic energy you need to escape. And it's a cool result that, when you're in circular orbit, you actually have half of the amount of kinetic energy you need in order to escape the pole of Earth. All right, well, that's that. And when we get to class, we'll have an opportunity to practice applying gravitational potential energy and escape velocity to a variety of problems. And I look forward to seeing you then. Bye.